In this problem, we start with a reminder of the energy level formula in the derivation of the Bohr atom. So the Bohr atom is this model of the hydrogen atom. We started with the quantization of angular momentum, and we arrived at the quantization of the radii of the electron orbitals and the quantization of the energy levels, which is the little formula that we're looking at here. So it turned out that the nth energy level is 1 over n squared times E1, where E1 is the ground state energy of negative 13.6 eV. Then we're asked to use this formula to find the first 4 wavelengths of the Paschen series, which is decays to the n equals 3 state of the hydrogen atom. So we want to look at a decay from n equals 4 to 3, 5 to 3, 6 to 3, and 7 to 3. Those decays are drops in energy for the electron in the hydrogen atom, and so they correspond to photons that are emitted in the spectrum of hydrogen. So we've already done one of these problems by using Rydberg's formula, and I think to make the approach here a little bit distinct, I'm just going to list the energy levels for the hydrogen atom all the way to the 7th level. So there's our ground state energy. Remember, this is negative, and the 0 reference point of our energy scale here is when the atom is ionized, when the electron is completely removed. So this is the deepest an electron can sort of be in the potential energy well. And as I go to higher energy states, I'll get closer to 0. So E2 is going to be 1 over 2 squared times negative 13.6. This gives me a negative 3.4 electron volts. And we go on like this until we have all the ones we need. So you should notice that we're getting closer and closer to an energy of 0. That's where the atom would actually be completely ionized. And another thing to notice here is that the spacing between the energy levels just keeps getting closer and closer. So we're trying to list the first 4 decays to the n equals 3 state. And of course, these have to happen from a higher energy state. So our first one is our decay from the 4th state to the 3rd state. And I can express this as the drop in energy for the electron. So I'm going to do E final minus E initial. And that's an energy drop of negative 0.66 electron volts. This means the photon that's released is going to carry away that energy. So it's a photon with 0.66 eV of energy. Well, I want to relate this to the wavelengths, and so we use our standard formula. The energy of a photon is hf, but I could also write that as hc over lambda and solve for lambda. And we've been used to using this approximation that hc is about 1240 eV nanometers. This is so convenient because it's all in the units that we're using. And the energy we're talking about is 0.66 eV in this case. The electron volts cancel. I immediately get units of nanometers for my wavelength, so that's wonderful. Into 3 sig figs, I get 1,880 nanometers for my wavelength. Now we know the longest visible wavelengths are somewhere around 700 nanometers. So this light has longer wavelengths than that. It's less energetic than that. And so this light is in the infrared band. That's light that's off the red side of the visible spectrum. So that kind of knocks out this part of the problem. Comment on the type of light emitted in the Paschen series. And we'll see how it goes for the rest of them as well. All right, I should be a little more brief with my transition from the n equals 5 to n equals 3 state. My final energy is going to be the same thing, negative 1.51 eV. My initial energy for the n equals 5 state was negative 0.544 eV. This gives me an energy transition of negative 0.966 eV for the electron. And this means the photon is going to run off with 0.966 eV of energy. So let's go straight to our wavelength formula. That's 1240 eV nanometers over the energy of the photon, which again is positive. The electron had a drop in energy. The photon runs away with that energy. Into 3 sig figs, I get 1280 nanometers. Again, this is an infrared photon. Okay, the 6 to 3 transition gives me negative 1.13 eV of energy lost by the electron. So the photon runs off with 1.13 eV of energy. And I get a wavelength of about 1100 nanometers, again, infrared. And finally, our 7 to 3 transition. Notice I'm seeing a little bigger energy drop for the electron because it's dropping in from a higher energy level. Into 3 sig figs, I get 1010 nanometers. So just as a little bonus question here, this begs the question, are there any wavelengths in the Paschen series that are going to be visible? And our best chance of it is to drop all the way from the ionized state down to the E equals 3 state. Well, that's where the electron starts with an energy of 0, and it drops all the way to negative 1.51. And so the energy of the photon in that state would be the full 1.51 eV. That's 821 nanometers, and it's still infrared. So we conclude that all photons emitted from transitions down to the n equals 3 level in the hydrogen atom are going to be infrared. You may recall that all the transitions down to the ground state were ultraviolet. So it looks like only transitions to the n equals 2 state are giving us visible photons, which are responsible for the color of excited hydrogen gas. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.